Representation of a vector in terms of its rectangular components in 3 dimension. This is x-axis, y-axis and z-axis. O be the origin, and a vector A is represented in magnitude and direction by the straight line OA having direction from O to A. A perpendicular is drawn from A on xy plane. Perpendicular is AN and we connect O and N. From A we can draw a normal or perpendicular from Z, and a perpendicular is drawn from N on x-axis. This is the point N, and we can draw another perpendicular from N that is on y-axis. A perpendicular is drawn from N, and NP is the perpendicular. NP is the perpendicular on x-axis. NP, not NB, it is NP. NQ is the perpendicular from N on y-axis, and AC is the perpendicular from N on z-axis. Vector AX is the rectangular components along x-axis, and vector AY is the rectangular component of vector A along y-axis, and vector AZ is the rectangular component of vector A along z-axis. Now we can denote the direction of ON from O to N, and direction of NA from N to A, and direction of CA from C to A. And here NP will have the same direction as that of the straight line OQ. So always try to denote the direction. That means direction of two parallel lines will be same, two opposite line will be same. Let a vector, let vector AX, comma vector AY and vector AZ be the rectangular components, of vector A along x, y and z axis respectively. Using parallelogram law of vector addition. Using parallelogram law of vector addition, in the parallelogram ONAC, we get vector OA equal vector ON plus vector OC. That means the diagonal will be equal to the sum of two adjacent sides, where vector OC is equal to vector AZ. Vector OA equal vector ON plus vector AZ. equation 1. This is equation 1. Again, according to parallelogram law of vector addition, parallelogram law of vector addition, vector addition in parallelogram OPNQ, vector ON means the diagonal will be sum of two adjacent sides, vector OP plus vector OQ, equation 2. That means using parallelogram law in parallelogram OPNQ, the diagonal ON will be equal to sum of the two adjacent sides OP and OQ. This is equation 2. In place of vector OP we can write vector AX, and in place of vector OQ we can write vector AY, which is vector ON. Therefore, this is equation 1. Vector ON is equal to vector AX plus vector AY. Now, putting equation 2 in equation 1, we get vector OA equal vector ON plus vector AZ. Now, vector ON is from equation 2, or using equation 2 in equation 1, putting the expression of vector ON, that is vector AX plus vector AY plus vector AZ. Vector AX plus vector AY plus vector AZ. Vector OA can be written as vector A, and in place of AX, this is vector AZ. In place of vector AX we can write, so finally we get vector A as vector AX plus vector AY plus vector AZ. Equation 3. Equation 3. Now AX is equal OP, vector AX is equal vector OP is equal mod vector OP I cap is equal to AX I cap. Vector AX equal AX I cap. That means if we denote a unit vector having magnitude 1 along x axis, that will be I cap. Unit vector along y axis is j cap, and unit vector along z axis is k cap. Similarly, vector AY equal to AY j cap, vector AZ equal to AZ k cap. Where I cap, j cap and k cap are the unit vectors along x, y and z axis respectively. Therefore, vector A equal AX I cap plus ay j cap plus az k cap. This is the expression of vector A in terms of its rectangular components ax, ay and az. In this way, vector A is represented or is expressed in terms of its rectangular components ax, ay and az in 3 dimension, in 3D.